Jnanam paramam dhyeyam. Knowledge is supreme.
Now, next problem is you write the x, y and x, z and also x square minus y square as the component of second rank tensor. So, you need to recollect here in this problem, problem number 3, that in the tensorial notation these if I write t q comma k, sorry, t k comma q, okay, these can be written in terms of the spherical harmonics L, m, theta, phi. So, these things I think you all know, you all have seen in your regular class that the tensorial notation or these tensors can be written in terms of the spherical harmonics. So, here you can write, if I write here k comma q, this is k comma q, okay, theta phi, and this tensor, for example, now I have 2 q. This can be written as, so this is a rank 2 tensor. When I write k is equal to 2 implies it is a rank 2 tensor, okay. So, this is a rank 2 tensor and one can obtain the rank 2 tensor by taking a tensorial product of the two, that is A sum 1 comma q times B 1 comma q, and you take a sum over. So, this is q1 q2. So, if I take sum of q1 q2, so q1 can take any values and the coefficient here can be written as, so this can be written as the coefficient which I missed here, q1 q2 and k q, or another way of representing this would be 1 1 2 q1 q2 q. So, this q corresponds to k as 2, q1 corresponds to k as 1, q1 corresponds to k1 as 1. So, in order to write the tensorial representation, we need to have a matrix, or we can write it in terms of a matrix. But before that, just remember how the coordinates or x, y, z are represented in terms of the irreducible tensors. So, in order to calculate the irreducible tensors of the product of the two irreducible tensors, we need to know how they are represented in terms of reducible form. So, reducible form you will write in terms of irreducible form, and then you can prove this W or omega is product of these two irreducible tensor are scalars. So, actually they are in the next problem you will prove that they are scalars. So, that will be a generalized statement which we will see in fourth problem. So, point to remember here is, if I have A, okay, I can write A11 as minus x plus iy, minus x minus iy, sorry, minus x minus iy, and A1 minus 1 as minus x will become plus x. So, this will be plus x minus iy. So, in general let me write here A1 plus minus 1 is written as minus plus x minus iy, and A10 is the z component, Az. Okay. So, with this we can actually evaluate the direct way in which you can actually write x, or here you can just write it as z. Okay. So, since I am writing in terms of the radial coordinate, where a is some radial coordinate. Okay. So, when a is a radial coordinate, you can write in terms of x plus iy, and a 1 0 will be the z component. If I am writing a as some momentum operator, then it will be px, py, pz. If I am writing in terms of vector potential, it will be ax, ay, az. Again the form will remain the same. X will be replaced by ax or px, y will be replaced by ay or py, z will be replaced by ay or az or pz. So, this definition you have to keep in mind before you actually start doing the problem. So, we will go to the next point, wherein I will write this T. Now, here K is equal to 2, which is a second order tensor, rank 2 tensor, and Q is equal to 2. So, this I can write it as A11, B11. Okay. So, we take the example wherein you have a Q cross Q, or 1, 1, 1 as the component. So, Q, we have a constraint over Q, that Q should be equal to Q1 plus Q2. So, we can have 1, 1 over here. Okay. So, with this I can play around, I can write this. So, if I assume that these are the radial component only, A goes to a radial component, B is also a radial component, then my A 2 comma 2, when I write in terms of the previous thing which I showed you, 1 comma 1. Okay. So, I will have simply this as x plus iy the whole square, correct. So, I will have x plus iy into x plus iy, correct. So, this will be minus x minus iy. So, when I have this, we square it, I get x plus iy the whole square. Now, you know how we can write this 2 comma 2 as x square minus y square plus 2i xy, and similarly 2 minus 2 is written as x square minus y square minus 2i xy. From this simply you add these two, and when you add these two you get the value of x square minus y square. So, your x square minus y square will be 1/2 T2 2 plus T2 minus 2. This is what is expected of you to calculate. In the similar manner, using the same line in the same stream, you can calculate the values of x, y and x, z. So, this is another DIY, okay. You can do this, you have to make some guesses. Now, x and y you can see directly from here, I can subtract the two and obtain. So, I have already given you for this. Now, think how will you get for x, z, okay. Just think and you will get it. The next part of the problem, whatever we have done in this third problem, a similar line of thought will help you to solve the fourth problem. So, when you can start by, again the reminder to you, note that T I had written in the previous case, but again I wish to rewrite it, minus plus x minus iy T1 comma 0 is nothing but the z component. And remember, how will I write the dot product of A dot B? Whenever we write in Cartesian coordinate, how do we write? We write it as ax px plus ay by az bz, right. So, let me write it for you all, ax bx plus ay by plus az bz. This is the way I write. Now, let us do it in terms of the irreducible tensors. This can be done you have to think a bit and convince yourself what I am writing here, A1 minus 1 B11 minus A11 B1 minus 1 plus A10 B10. So, this I am not getting blindly, you have to just rewrite this, or you can start by writing the form in which you can have A and B, the possible values of A and B. So, A can have the tensors or the terms which involved with A are 1 minus 1, 1 0 1 1. Similarly for B, and you have to make a combination such that you get Ax Bx plus Ay By plus Az Bz. So, this you can try how this transition, or the other way around, you can start with this and get the term. Now, let me write this term in the compact notation. So, what is the compact notation I can think of here is A, I have 1 is there in all and Q is changing, Q is minus 1 or 1 or 0, either it is 1, 0 or minus 1. So, I can take summation over Q going from 1 to minus 1 to 1 times B 1 minus Q. You can see here that B is taking different value. So, I write it this way, and I have a factor of minus 1 times Q. So, I will have this in the form of compact notation. So, I have 3 terms. You can again check this to this step, it is very easy. And in order to prove that the A dot B is a scalar, what you have to do is you have to write the scalar product in terms of the irreducible tensor. So, now you know that this is a reducible tensor, reducible operators or terms which can be, we have written it in terms of irreducible representation. And I give you a hint that you use, if you can show, this was called as omega, right, this term in the expression in the question is omega. If you can prove j plus minus omega is equal to 0 and jz omega is equal to 0, then you are indirectly showing that omega is a scalar. So, when you have a commutator of an operator with a scalar, then it is always 0. This by notion you know. But to do this job, you should know what is the commutator of j plus, j minus and jz with these irreducible tensor. So, I will give you another hint which would make your problem much simpler. So, this is j k comma q is q h cross. We have come across this before also, you have seen this in problems where we have linear operators, and we discussed about these kind of commutator brackets. So, it is not a new thing for you, but just trying to recollect it for you all, so that you can directly apply it in the problems. Here I am not sure about the plus and minuses, so I just write it as C plus minus. You will have this h cross square root of q k plus q into k minus q plus or minus. So, you have to check that part, okay. But you have already with you, but this is just a hint, an outline, so that you go about for the fourth problem. Okay, fifth problem at this point we can actually skip, but since it is a part of the tutorial, I will discuss it. If it is not very clear, then in the next tutorial we are going to repeat such exercise, such problem. So, you need not get much panic if you are not sure what is going on, because Wigner-Icart theorem will be discussed in the coming lectures. So, there will be a recapitulation of everything in the last tutorial. So, the problem given to you is in a rotationally invariant system in 3 space dimension the matrix element of the z component of the dipole moment, that is half the z component of the dipole moment is given to you as some a value, and in terms of a we have to find out the x component of the dipole moment and some hint is given to you. Okay, before we actually attack this problem, what I want to say is that I will what I will do here is I will give you a, one example wherein you will understand what exactly is being done in this problem. So, the thing is that when you are doing some measurements, you are given the output of the z component, the experimentalists give you the output of the z component, and you want actually when you are performing the experiment you want the data of some other quantity. Here you have pz. So, in order to obtain pz you cannot make the measurement, but there is some way in which you can obtain px. So, px can be obtained by using Wigner-Icart theorem. When you use Wigner-Icart theorem, you will not get the exact value of the observable, mind you, but you can rewrite in terms of the known observable. So, that means that in this problem you can write pz such that, or you take the ratio of pz and px. So, here you are given a hint that px is 1 by root 2 times p plus p minus. So, there is a minus sign here and p minus. So, when you are attacking such problems, you have you can write, let me call b as half px half. Okay. This is what is asked, right? Here there is a minus sign. Okay. I have skipped the commas, but you can understand. So, this I can write it as p plus and p minus. Obviously, p minus will not act on this, p plus will act on this. So, this will be the this will only give us the non-zero contribution. So, this will give me minus half p plus half minus half. Now, again you have to write this in terms of irreducible tensor. So, when I write this in terms of irreducible tensor, what do I obtain? I will have remember I will write here the Wigner-Icart theorem, or let us move first to the irreducible tensor part and then I write the Wigner-Icart theorem. So, this would be nothing but half here I will have a 1 half minus half. So, with this you can move further and write the Wigner-Icart theorem. So, Wigner-Icart theorem is WE theorem, I am writing the short form. WE theorem is that you can write this half, or I can write in terms of m and m1 and m2, j2 m2 t k comma q j1 m1 can be written as the constant part j1 and j1 m1 k q, here you have j2 q m2. This is a k, this is j2, this is q and this is m. So, I have j2 m2 j1 m1 and this is my irreducible tensor, and I can write in terms of two pieces, one a constant part, another which will be of the form of CG coefficient, which you can evaluate. So, this will be j1 m1 k j2 q m2. This is the way it is written down. So, for the case of pz, that is my pz was half Pz half half divided by half half Px half minus half. This is A by B, and this quantity here, this can be reduced or rewritten as, I will have two terms which exactly cancel these constant term. So, when I write A by B, I will have half half 1 half 0 half. Okay. Just take care that here I have k is 1, q is 0. So, this is the result, and on the left obviously I have half and half. Okay, I have written that. So, this is the bracket. Then I have half half, and here I have 1, then I have a half, then I have a 1 and a minus half. Okay. So, these quantities you can evaluate. So, now our B would be, you have to evaluate these using the CG table. You can use CG table and evaluate these quantities. So, here your K is 1 and your Q is also 1. Okay. So, B you will find that it is equal to A. So, if this is not very clear, you will get the essence of this problems in the next tutorial. So, let us stop here and we will continue for the next tutorial in the next session, which will be the final session.